Hi, people. Just a few moments. We'll be starting. So once again, another normalization. Last time we just started on normalization effort, so let's continue. Normal forms are something like quality cells, some metrics, not metrics, just quality cells. So we try to mark our schemas, assess its quality, and say, oh, it's quite good. Second normal form, oh, it's better. Third, or that's wonderful. Fourth normal form, and so on. To improve the quality, we have synthesis algorithms that move us to further from lower normal forms to better, to higher normal forms. And we may construct high quality schema by two main ways. First way is to start with universal relation. Universal relation is like paper document, paper table. And we have a table with some columns, and let's let's create table of the same structure in your database, they say. So in many cases, this relation is not good. So it may be not even in the first normal form. So we may start and then apply synthesis algorithm or just decomposition algorithm. We'll see. So just few anomalies, 3 kinds of anomalies. Connect that anomalies that may happen in databases without normalization. And all the normalization thing is aimed at writers support. So if we have multiple writing processes, data creators, that performs inserts, updates, deletes, to manipulate with data, then normalization is good for them. So we try to get rid of some anomalies, some problems with updates, with inserts, with deletes. But if our most of our processes are readers, then we'll not be happy with normalized system. So for readers, we need to denormalize everything. So every reader may just come with small query and have its results structured as they want. So to make things easier for readers, we need to denormalize. To make things easier for writers, for data creators, for data producers, we need to normalize it. So we can't say that normalization is a silver bullet that lead everyone to happy state. So that's not the case. Normalization is for updates, mainly if our system is need to consume updates and inserts and everything. So normalization is better. So anomalies, update anomaly. What if Socrates? What happens when Socrates moved to a different room? We need to change this room number, and here and there and there and everywhere. So if we have table of professor and lecture, that this professor delivers this lecture. Each lecture is delivered by a single professor, but the same professor may deliver multiple lectures. So we have, if we store everything about professor, not just person number, but name, room number, level, together with person number, then we need to, at the moment of update, we need to reflect this single fact. Socrates' room number is now 227. Just single fact. We need to change here this value and that value and that value and multiple values. If we want to change Popper into full professor, then we need to go to every record where we have Popper and change it into full professor, full professor, full professor. So that's an anomaly, as we can just there is a possibility of forgetting. So we may just skip some records in this case and don't change by some accidents or by something. So if we need to store our data or introduce changes, the same change to multiple places, to multiple records, multiple cells of table, that may then we put our data at risk of non-consistency. So data may be changed differently. And let's say Socrates' room here is 226, and in another record 227. And who to trust? So That's update anomaly. Insert anomaly. What happens if some person, baseman, is elected as a new professor, but without lectures at the moment? So we need to put it here, but we have no enough data. So insert anomaly is about situations that to put data in this table, we need to have full knowledge about both professor and lecturer. If we have some only data about professor, that's not possible. If we know only about lecturer and not professor, that's not possible too. So insert anomaly is about need to have all the data to store. And delete anomaly is the same. If we delete, let's say Popper, then we'll lose all the data. We need to delete at the same time. We need to delete all the lectures of Popper. So removing this record will remove their Wiener Kreis too, not only professor data. That's delete anomaly. The delete leads to removal of additional data. And then we come to idea of functional dependency and functional, I'm sorry. And functional dependency is a dependency. So we say that that beta depends on alpha if for every pair of records, if alpha fields have the same value in both records, implicates that beta fields have the same values. So we can see that A has a dependency to B, so B depends on A, as every time when we have the same value in A1 and then by B is the same. But B to C is not a dependency, as we have B2 with C4 here and B2 with C3 there. So we have that's not a dependency. By convention, we may write instead of set notation, we may just put it shortly in short form and say just C and D, and B depends on them. So yes, that's what we've seen about keys, that some group of columns alpha is a super key if and only if all the columns depends on this alpha. So that's just definition of super key. So if I have at least single column that doesn't depend on my wannabe key, then that's not a key. And some keys are just super keys and some of them are minimal. And minimal is such a key that we can't remove anything from a column list without losing its super key possibilities. So for minimal functional dependencies, we put a dot over arrow, and we call such a minimal key, we call a key, just a key. So we have super keys and just keys or candidate keys that are minimal. So, and we can say that the whole column list, the whole table, the whole head of table is a super key, as every time have some values for all the columns. Those values are the same, so they depends on itself. So every table is a super key for itself, but we don't need such a trivial dependency. And trivial dependencies are dependencies where right side contains only fields from the left side, or just equal. A to A is trivial. AB to A is trivial. So ABCD to BC is trivial. So ABCD to ABCD is trivial too. We don't, trivial dependencies don't deliver new knowledge, so we don't need them. We need only non-trivial dependencies. So let's see at how to find columns that are keys. If I look at this table, I have towns, and I have regions, and area codes, and population. And I say, oh, town. Oh, I have two different wobble tones. In different regions, that's okay, with different area code, different population, so they're just different, but with the same name. That's sorry. So name of a town is not a key. It's the same name in different regions. So it can't be a key. But let's combine, let's check name and region. Wobbleton and R1, area code is this. Wobbleton and R2, area code is another. So yes, name and region is unique. So every time we can meet some combination of name and region, then area code is just is unique. Oh, yeah.
We can't hear you actually.
I know, I'm just not speaking. So name and region is possible key. As we can look at this table and not just look at this table, but we means if we know that in single region it's not possible to have towns with the same name, then we have dependency of everything, like population and area code are dependent on name and region. And the same for name and area code. If we know that no same name for towns in the same area code, so that's it. So quite complex case, complex table. I have a professor table, person, name, person number, name, level, room, and city, and city address, and zip, index, and area code, and region, and population, and let's say administration. So Sorry. I need to mute it. I need to mute it. That's it. So if we know person number, and we know that's a number, that's unique number for every professor and every employee in university, then it means that if we know person numbers, then name is unique for this number, and level is unique, and room is just single room, and region and address and population and everything. So person number determine everything else. Another, that's one dependency, and everything from the right side depends on everything on the left side. So let's say room depends on person number. That's just one dependency. Let's say region of professor's home, professor's house depends on person number, and so on. Another functional dependency is that if we know city and region, then population and area code is just unique. So population depends on city and region, not on city, but on both of them. That's great. And if we know zip or postal index, then we may find region. Region is unique for every zip, and city and population too. So every zip, every index, postal index, is determines everything to the right, and vice versa. If we know region and city, but not the whole city, but address in a city, then postal index is unique for every house. So if we know house address, then zip file is unique. But in the same city, in some cities, we may have multiple zips, but every zip belongs to only one city. That's it. And for each region, we have its administration, and and every professor has dedicated room. So if we know room number, then person number is unique. So if I know person number, then I may determine room, and if I know room number, then only one professor may belong to this room. And we may infer additional dependencies if we see that room arrow to person number, then and arrow from person number to somewhere else. So everything, all the functional dependencies are transitive. So if I know room, then I may find person in there, unique value, and knowing unique value for person there, then I have name and level and administration, everything as unique values. And if I know a zip, I can find a region. And if I know a region, then I find administration. So that transitive rule of inference is possible. So it may add additional dependencies. So I may visualize it like this. So person number and room are both uniques, and we may use them as a key for a person, for a professor, interchangeably. And everything else depends on both of them, not on their combination, but just independently on room and independently on personnel. Everything level and name. And here we have some complex situations that zip depends on city, region, and address, and city and region depends from zip. And this combination of city and region determine area code and population, and region, only region, determines administration. So that's a picture of all the functional dependencies. We inferred something. So probably our customer from university university people, they told us that that's a situation. That's our dependencies from real world, from our domain. And then we infer something extra. Armstrong axioms allows for inference of additional functional dependencies, provided some set of functional dependencies. Some of them are quite, all of them are quite simple, and 3 of them are basic. And using only these 3 axioms, we may infer everything. And some other rules, that's not axioms, that's technically speaking, that's rules of inference. That's not axioms, but they call this axioms, and 3 basic axioms. Reflexivity. If beta is subset of alpha, then beta depends on alpha. So every subset depends on the whole set. Alpha is A, B, C, and beta is B. So that's it. Special case alpha depends on itself. That's called reflexivity. And we may generate some functional dependencies just out of this fact. Augmentation. If I have a dependency, I may augment it with the same column or pair of columns on triple columns, gamma, and gamma is a set of columns, may augment it to the left part, and augment right part. And this notation means a union, set union. So if beta depends on alpha, then adding something to the left, gamma, don't change it. So if beta depends on alpha, then it still depends on alpha and gamma. So every time when alpha and gamma is unique, beta is every time alpha and gamma is the same, has the same value, beta have the same value. And due to fact of gamma being here, we understand that gamma on the right side depends on itself. So we don't care for alpha. Every time when gamma is set, then gamma depends on it. So we just have a unique value. So augmentation is quite simple too. We may add columns to the right and to the left. And transitivity is transitivity. Beta depends on alpha, and gamma depends on beta. That means that gamma depends on alpha. That's transitive. Some other rules about union. So we may, if we have alpha to beta and alpha to gamma, then we may draw it or just represent it as alpha to beta and gamma. And decomposition. Step back. If we have that's union and decomposition, if we have such a rule, then we may convert it in a pair of rules. With or not or, with and between them. And some other rule, rule called pseudo transitivity. If alpha to beta and gamma and beta to delta, that means that if we add gamma to alpha, then we'll have transitivity. Alpha and gamma to beta and to delta. So that's another kind that we may add gamma to the left side, and then we have something like transitivity. So, but beta should be here and there in both rules. Let's check additional rules, some of the additional rules, how we can prove it. Alpha to beta and alpha to gamma, and claim that alpha to beta gamma. Let's prove it. Alpha to beta, that's premise. Augmented with gammas, alpha gamma and beta gamma. Alpha to gamma, that's another premise. Augmented with alpha alpha to the left and alpha to the right. But we don't need to write alpha twice, so just alpha. That's another way of fragmentation. And now transitivity alpha to alpha gamma, and from alpha gamma to beta gamma. That means from alpha to beta gamma. That's application of transitivity rule, quadrant demonstrandum. So just simple checking with augmentation and transitivities. Reflection is quite not frequent. Idea or concept of attribute closure is just all the attributes. If I have a set of functional dependencies and starting set of attributes, all the attributes I can reach following arrows. Let's say I have this situation and I start with zip. What can I find? From zip, I go to region. I can find region and city and population. Okay. Knowing region and city, I can find population and area code. Great. Knowing region, I can find administration. Region, city, address is unknown. Person number is unknown. That's all. So starting with zip, I may reach zip, region, city, population, area code, and administration. So that's it. I can. That's an attribute closure. Starting with zip, I find zip closure. So attribute closure or closure of attributes is a set, such a set A alpha plus, such that all the attributes that depends on alpha. And the dependencies may be inferred. So transitively, it's essentially transitively, or directly or transitively depends on alpha. How to build it? Just mechanism is the same. I start, my result of closure is alpha, starting. All the starting fields due to reflexivity are reachable from themselves. And then while result has changed, and result has changed just now, I loop through all the functional dependencies. And let's say that's dependency of kind beta to gamma. And then I look here, if beta belongs to result, then I may apply this. So I already have result is all the columns that are uniquely defined by our starting set of attributes. So beta is uniquely defined, then that's possible to add gamma to result. That's due to transitivity. And I repeat it and repeat it and repeat it. I loop through all the functional dependencies, and then again, and then again, and then again, until nothing, until my evolution stops, or just all the fields are in result already. If I collect all the table fields, then if I collect all the table fields, then I need to stop too, or result stop changing. We can prove it that it terminates, that it deterministic. To think about termination, we need to see that for each rule, one option is to change result, and another option is not to change result. If nothing change result, then we stop iterating due to result has changed condition. But if result is enriched, then we can't enrich result more than with all the attributes of a table. So on each step, either we add something to result, and we may perform this action only as many times as there are columns in a table. So that's finite. And or we just stop a result, stop changing. So final result is already found, so it terminates. And at an algorithm of going back, finding minimal basis. Essentially, I have a set of functional dependencies like here, and then I add additional functional dependencies, infer them, and enrich my set. But why do I want to add additional functional dependencies? Everything here may be inferred from and is inferred from these dependencies. Much better is to find, maybe I may remove something, so I'll have smaller number of rules. So to perform inference, to perform, let's say, this process of closure building, if I have smaller number of rules, I need to loop through small set of rules for each. So I don't need to check multiple rules, and they give me nothing new. So another algorithm is, and another concept is minimal basis. And minimal basis attribute closure is a set of attributes, and minimal basis is a set of functional dependencies. So, and minimal basis, how to check that some basis is a minimal for another functional dependency set. First, I need to check that the closure of attribute sets are the same. So if I start with functional dependencies of F and try to find closures, and then I search for build all the attribute closures for FC, then they will be the same. So I can't remove dependencies that took part in closures, that change closures. Second thing, all the functional dependencies in minimal basis are minimal. What does it mean? That means if I have alpha and function, if I remove from minimal basis, remove this, I'll remove rule, I'll remove a dependency, then result FC minus alpha to beta. And all the attributes besides alpha minus A, alpha minus A follows beta. So result, so I can't remove no attributes from functional dependency without making it not equivalent to original functional dependency. So I can't minimal functional dependency is such a dependency that I can't remove anything from left side or right side without making it not functional dependency. And there are no two functional dependencies with the same left side. If I can find them, I need to merge them, or union. We have union rule. If I have A to B and A to C, then I need to merge it and say A to BC. That's a way of building minimal basis. And we can see an algorithm of computing. Of the minimum basis. First step is reduction of left sides. So if I have a functional dependency from alpha to beta, and A is an attribute from left side, I try to remove it from alpha and try to build a closure of all the attributes from the left side without alpha. If beta is still here, that means that we can find unique, we can move by, we can reach using arrows from alpha without A. Beta is reachable from alpha without A. That means we don't need that alpha on the left side. We have another way to reach B. Then we replace alpha to B with alpha minus A. So we remove, reduce left side. to beta. The same thing is right part, is with right part. So if we get an attribute B from beta, and then build, start with alpha and try to use functional dependency set, remove alpha to beta and remove alpha to beta without B. So we're trying to remove every attribute from the right side and check if we can reach this removed attribute B. If B belongs to closure, then we don't need this rule anymore. So we replace alpha to beta with alpha to beta minus B. So we check every attribute to the left and to the right and check, is it still reachable, that removed attribute from the right, is it still reachable from everything that's left in our functional dependency set. So that's reduction. Then we'll perform a cleanup. If we reduce everything on some right side on some functional dependencies, that means we'll have alpha arrow to empty set. Then we don't need such a functional dependency. That's trivial. Empty set is empty set depends on everything. And then we merge or union all the rules with the same left side. So just small algorithm, try to remove every attribute from the left side of each dependency and check if right side is still reachable. And then remove it. And remove each attribute from the right side and check that attribute is reachable by everything that's left. And if yes, then we can remove it from this rule. So let's look at the same functional dependency list. Oh, sorry. Oh, functional dependency. So we don't need to prove it, but proof is quite simple. So just applying that's a proof of left reduction. If the first part of reduction, that's left reduction, we may prove it quite simply, and the right side is proved the same in the same way. So let's return to our bed schema. Our bed schema consists of multiple tables and may lead to update anomalies, insert anomalies, delete anomalies. How to get rid of those anomalies? We need to decompose it. And problem with insert anomaly and delete anomaly is in that this table, this relation, combine different concepts. It stores both professor's data and lecture data. And that's about delete. If we delete only professor data, we need to delete lecture data too. And if we want to insert only professor data, we need to insert lecture data too. That's anomalies of insert and delete. That's bad relations that combine several concepts. So we need to decompose them into multiple relations so that each concept will be in single relation. So we have a table, we have a relation, and then we decompose it in multiple relations. And the decomposition need to follow two properties. First, that decomposition should be lossless. And lossless means that if I get all the tables, the result of the decomposition, and perform natural join of them, and perform natural join of them, then I'll have my result of that natural join is my original table. Speaking about data contents, so every time when I join result of decomposition, I can rebuild my table, and not only rebuild all the records, but I will have nothing extra record, no extra records. So that's not only lossless, that's also nothing new, decomposition with no new records. And preservation of dependencies, that's another property. If I build built a closure for if I build everything that can be inferred, so I have just dependencies for my table, and then I need, and plus is everything that follows that can be inferred from these functional dependencies. And if I combine all the functional dependencies of smaller tables, then result of inferring everything that follows from this set should be the same. That means that I can't decompose, my decomposition can't cross dependencies. If something in single dependency, A and B and C follows D. So A and B, A, B, C, arrow D. That means if I have such a dependency, that means that A, B, C, and D should need to be in same table anyway. So all other ways just split my columns, and I can't set a functional dependency between two different tables, between two different relations. So all the columns in each dependency need to be stored in just single relation. That's what comes from preservation of dependencies. It means all our dependencies need to be preserved. We can't essentially delete them. So when is a decomposition is lossless? Let's say we decompose into just two tables, and first table R1 is just a projection on some columns, on R1 columns of R, and R2 is a projection on another column set. Decomposition is lossless if intersection of columns R1 and R2, R1 and R2 independently depends on intersection, and intersection is essentially key. So if that's possible, then our decomposition is lossless. If not, that's not. So both R1 and R2, they need to have the same fields, at least single column. Here, if I have all the columns of R, then R1 is some columns called beta here, and some other columns called alpha. And R2 is columns beta 2 and other columns of gamma. So that intersection is a key for both sides, for all the records. So knowing beta value uniquely define single alpha values and all the gamma values. So what does it mean, this dependency? The dependency means exactly this. So example, small example, I have a drinker people who come to pubs, and their names are in the column guest, and a beer they prefer. So in pub Kowalski, we have Kemper, who is a guest, and he likes pills. And Eichler in the same bar as Hefeweizen. And Kemper likes Hefeweizen too, but in another pub. So that's a table. If I try to decompose it, essentially it combines two concepts. One concept is a relationship between pubs and guests who come where. So Kemper likes both Kowalski and Instead, and Eichler come only to Kowalski. And which beers different people like. So two different facts: who come where, to which pub, and what beer like which guest. That's different. If we project it on pub guest and beer, and guest is in intersection between them, then we have this table and that table, and let's check that guest, and let's check it. So just 2 columns from here, 2 columns from there. That's a decomposition. And let's look that if we try to perform natural join to rebuild our original table. Let's perform natural join. What's the common column? Guest is a single common column. So natural join will find all the records with the same values in guest columns. Kowalski, Kemper, Pils. Kowalski, Kemper, Pils. Here it is. Kowalski, Kemper, Hefeweizen. Kowalski, Kemper, Hefeweizen. Kowalski, Eichler, Hefeweizen. Okay. Instead Kemper, Pils. Instead Kemper, Hefeweizen. 2 records more. And if we compare here, we have red records that are results of lossy conversion. So that's not a loss of information. Essentially, that's generation of additional data that wasn't due to decomposition. Decomposition led us to magically generating new data we didn't have. So that's not good. We don't want such a situation. We know that Kemper come to Kowalski and drink pills there, probably. And Kemper come to Instead and drink Hefeweizen there. And we don't know what happens, that these are real facts. So results are different, and that's lossy decomposition. Even if, and so the decomposition is lossless if intersection is a key for both R1 and R2. So let's check. Key. What's a key here? Kemper, Eichler, Kemper. That's not a key. The same guest, Kemper, twice. So that's not unique. That's not a key. Kowalski. Oh, pub is not a key. So intersection is a guest, but guest is not a key here, and Kemper, get is not a key here. So our lemma is doesn't hold. So intersection of column lists is not a key for both columns. So we can't tell that decomposition is lossless. And that's not lossless. So essentially, drinker has just single dependency from beer depends on compare of pub and guest. So drinker like different beers in different places. And guest is not a functional, is not a key for, we have no dependency of guest to beer, and we have no dependency of guest to pub. The same guest has different beers. Kemper Pils, Kemper Hefeweizen. The problem is Kemper likes different beer in different pubs. Another table, and we try to decompose it losslessly. Parents, father, mother, and child. And we make one table of father and child, and another table of mother and child. And then decompose it. Oh, that's decomposition, and let's recombine it. And let's see a child column, and child is intersection. And child else it's evidently a key. So each child has just single father. For each child, we have only one father. Father is not a key. Father have multiple children, but child is a key here. And the same for mothers. Each child has single mother, so each child has just is a key here. So lossless decomposition lemma about that intersection of columns is a key for both tables. Does holds here, and that means that our decomposition is lossless if we join it else to else, Johan and Marta, Theo and Theo, Johan and Maria, Cleo and Cleo, Heinz and Marta. Even if fathers and mothers as duplicates, but children is unique. So both criteria of lemma are met: child to mother and child to father, and child the key of all the relations. Without, so that's if we have such a key, then never hurts to decompose. But probably we don't need to do it like in this case. We have a table parents with a key of child, and everything depends on child. So we have a key of child, mother depends on child, father depends on child, and father and mother doesn't depend on each other. So we don't need to split this table. We don't get anything new. We don't get anything new, and we don't have performance maybe or some other benefits. I'm sorry, just a few moments. Okay. So that's for lossless decomposition. For preservation of dependencies, let's see. We have functional dependencies, and if we decompose our table into multiple tables, then our decomposition, our functional dependencies will be decomposed in some sets of functional dependencies for each table. Let's say we have a table of zip codes: street, city, region, and zip. And functional dependencies here: city and region depends on zip, and zip depends on street, city, and region. Let's decompose, for example, into streets and cities. Each street has a zip and street, and each city has zip, city, and region. If we check for lossless, let's have what is intersection. Intersection is zip, and zip in zip, city, and region is a key. Due to first functional dependency, we know that city and region depends on zip. Okay, and in second, zip and street, we don't know whether street depends on zip, but we may think that street belongs to city, and that means that probably yes, probably street depends on zip as transitively, as street depends on city. But about functional dependencies preservation, let's see. So different cities with the same name in different regions, and streets with the same name. So we have a street in Wobbleton in R1 and the same a street with the same name, a street in Wobbleton in R2, and another street in R1's Wobbleton. All the zip codes for all the streets are different. And then we split it, and zip and street here, city region and zip here, and right table of cities is quite correct. In Wobbleton R1 with zip code of this, Wobbleton of O. We have Wobbleton and R1, and zip is a key. So for each zip, we have cities and regions unique. For every zip, we have some pair of, we don't have multiple zip records with the same zip. And for streets, we have both zip and street, both are key. So that's correct from the point of from the losslessness. But we have some functional dependencies: street, city, and region, and zip depends on their combination. And now we have two tables, and we have all the four fields in at least single table. We have no table with all the fields. Closest one is cities, but it doesn't have street. So that problem. So we lose. Our dependencies are not preserved. We have one dependencies that can't be enforced. So that's possible to insert inconsistent tuples. And let's see. We may go to cities and add Wobbleton from R2 and say that have a zip of this. Nothing strange. Okay, so for zip of 8108, this postal index belongs to Wobbleton from second region. And then we go to streets table and add completely legitimate record that a street belongs to have postal index of the same value of 81008. Okay, so both changes are quite simple and possible in both tables. But let's look at the merging. If we merge these two tables, then we'll get that Wobbleton from R2 has a street with zip code. Let's check city, region, and street. Zip is unique. City, Wobbleton, R2, street the same. Zips are different. So our dependency of city, region, and street to zip is violated. But we can't check it. We just insert new records. All the records are possible. Record here, record there. But our dependency is not checked. And when we rebuild our table, then we can find extra records, and not just extra records, but extra records that violate our dependencies. So that's the second not a problem, but second idea that we need to not to split tables that don't preserve dependencies. So we can't split this table. Street, city, region, and zip need, as we have such a functional dependencies, we need to store it, this table. And second, with a key of 3 fields. And then we need to add a table of cities with zip to city and region. So that's not just decomposition. We just we add new table. Our table is preserved to preserve functional dependency, and we add another table to make zip a key in that table. So this dependency may be checked. So that's a way. And so let's go to normal forms, the normal form definition. First normal form tells us that only atomic domains are possible. Okay, so only atomic domains. We can't put, let's say, else Lucy here, and we can't put lists here. We need to convert it this way. Every time, for every value of a child, we need to have distinct record. That's the idea of first normal form. So lists are not allowed, and complex data is not allowed. If you need to store complex data, you need to distribute it between multiple records. Second normal form. Table is in the second normal form if and only if every non-key attribute that don't belong to key is minimally dependent on every key. So minimal dependency means that it depends on the whole key. Let's look here. Student ID, lecture number, name, and semester. Student ID. Let's look here. So let's check non-key attributes. Name, Fichte. Fichte need to depend on the whole key. Student ID and number. Oh, looks good. So we can't find this rule violation. Let's look at Schopenhauer. Schopenhauer. Oh, it depends on stud ID and not on combination. We see that stud ID with this number with lecture number and the same stud ID with different lecture number. So Schopenhauer don't depend on the whole key, but only on partial key, on the first column from key. Every time when stud ID is this, then Schopenhauer is that. So that's minimal dependency. If we can remove some columns, then that's not minimal key for this column. So stud ID, student attendance, this table student attendance is not in second normal form, as name and semester depends only on stud ID essentially, and not by lecture number. And in Carnap we can see the same thing in 4 records. So this table violates second normal form, and second normal form means that every column if we have dependencies, then we need to have left side of dependency be the key, not part of the key, but the whole key. In some cases, yes, that's possible that key is complex. Key consists of 2 columns or 3 columns, and everything else depends on these 2 columns, on 3 columns, or something. That's possible. But we need to check. So second normal form may be violated only by complex keys, by tables with non-single attribute key. If you have just single attribute key, then second normal form is automatic. You can't violate it. So dependency is minimal from single column key, single attribute key. So solution is to decompose this table into 2 different relations. One relation is about attendance, student ID and number, and another is about student and name and semester. So essentially, we combine facts of students, data on students, and data on attendance. Try to put in here. We need to put in different tables, and this decomposition is lossless. So stud ID is a key. Oh no. So stud ID is not a key. It preserves dependencies. Dependence from stud ID to name and semester. Preserved. Between stud ID and number, we have no dependency. And stud ID and number. Yeah. If we return to entity relationship modeling, then a violation of second normal form is represented or may come from combining or mixing. If we have student, it's entity, and a relationship of a tens, many to many, we combine it in a single table. That's not correct. To mix entity and one to many, let's say lecture, then we can store who gives the lecture inside the lecture table due to one to this side, and that's not correct to store it to this side. So we need to separate entity and relationship if they are related as many to many. And the last thing for today, the third normal form. And third normal form is about essentially transitivity. So if table is in third normal form, if for all the functional dependencies, either at least one condition holds, right part of that dependency, dependency is trivial. So right part belongs to left part, A to B, alpha to B, and B belongs to alpha. One option. Another option, that right part is an attribute of a key. So if right part belongs to a key, that's okay, no violation. Or alpha is a super key. So everything in alpha, all the columns depends on alpha. If not, if I have a functional dependency that doesn't fulfill any of this condition, so B is not an attribute of a key, B doesn't belong to alpha, and alpha is not a super key, all the three conditions are not fulfilled, then alpha, essentially left part, need to be put in another table and represents a distinct concept. So it's not a super key here, but it has something that depends on it. So B. So we need to decompose it in this way. So let's look once again to this table. That's in third normal form, as person is a key, room is a key, and let's say zip is a key for city and region, but it's not in third normal form, as we have some transitive dependencies. Let's say address, all three columns, and they are not super key, address, city, and region, and zip depends on them. Or administration depends on region, and region is not a key. So let's check region to administration. I have a functional dependency. Region to administration. Administration don't belong to region. Administration is not a key attribute, and region is not a super key. So that's not a third normal form. So if I have some arrows that lead to non-key attribute and start somewhere from some part of, from some other attributes, not key attributes, then third normal form is violated. What does it mean? That means that several entities are mixed, maybe connected by relationships. Third normal form, second normal form, means that we mixed entity with relationship and let's say put gives into professor, but professor gives multiple lectures, so that's not good. And in third normal form, we mix not entities with relationships, but several entities, and probably connected with relationships. Let's say professor and city and region, and professor may be combined with lives. So professor lives somewhere. We may put city name to professor. That's okay. City belongs to region. Each city has a fields, has an attribute of region. That's okay. but we to store that professor, city, and region, that's not okay. Then we have professor as a key. Each professor has single city, okay, and region. And yes, region depends on professor, but region is also depends on city, and city is not a key, and region is not part of a key. So that dependence between city and region means that we need to extract it and store combinations, store data about city in another table where city would be a key. So that's an idea of third normal form. So we don't need to put everything in one table and implement relationships in separate table. Essentially, entity relationship modeling and all the rules of entity relationships automatically lead to third normal form if we follow rules of conversion of entity relationship in the relational model. Automatically creates third normal form tables. That's just not a surprise, but it's a good thing. We can check that every table that's in third normal form need to automatically is in second. That's quite simple. And the algorithm, let's look the last thing, algorithm of synthesis. I have a relation, multiple functional dependencies, and I need to essentially decompose it. Algorithm of synthesis, but result of decomposition, results in decomposition. I need to find such tables that decomposition is lossless, all dependencies are preserved, and all the tables are in third normal form. I have a functional dependencies. Without functional dependencies, that's not possible to check normal forms at all. If I have no functional dependency list, I can't check anything. I know nothing about transitivity. I know nothing about keys. So I have no instruments, I have no tools to check anything. So I need to have a list of functional dependencies. Minimal basis, compute minimal basis. And for all the records, I built, if in minimal basis, I have a dependency, all the columns in dependency should be put in distinct table. And due to the fact that all the dependencies, left parts are unique in all the dependencies in minimal basis, then I'll have just single table for this combination of columns. And all the columns go here, and key is alpha. So essentially, that's it. If I have a group of columns in R, that's a key, I need to put it, I need to store it in distinct table. If I build, let's say, a table of ABC and another table of AB, I don't need to store AB, so I need to eliminate. I don't need shorter, smaller table if I have bigger one with the same columns plus something else. That's just it. So synthesis algorithm looks for core of algorithm, look to every dependency and create a table that keep all the data from all the columns in that dependencies, left part and right part, and the key is the left part. So let's look at the same table. We have the same dependencies, and that means that I need to create one table, number one, with person number, name, level, room, region, and so on, and street, and don't region, room, city, street, and region. Then for zip codes, street, region, city, and zip. Room and person number is just table of two columns that already here, person number and room. So I don't need to create second table. It's eliminated by first table. It's inside. So second is eliminated. Third is new table for cities, city, region, population, and area code. Okay, new table. Region administration. I have region, but no administration. Okay, new table, region administration, and zip, region, city. Oh, it's here. Zip code, street, region, city, and zip. Okay, we don't need to to add this table. So result is 6 dependencies and just 4 tables. Some tables are additional. So that's it. I'm sorry for being too. So that's it.